And we're going to be discussing this question: how do rigid lithospheric plates move on the underlying asthenospheric mantle? And this movement is going to cause us to look directly at the presence of what's called the low velocity zone. Okay, so we've looked at this image before. That is from the textbook Earth, Portrait of a Planet by Stephen Marshak. And here we're looking at how seismic wave speeds change as we get deeper into Earth. The uppermost part, the lithospheric plates, are taken to be approximately 80 to 110 kilometers thick on average. Now, that is directly related to this seismic wave speed. On the right-hand side, the red line is showing us the velocity of the P primary, or the first wave to arrive, usually, although not always. And this is the compressional wave. And this wave changes in velocity from about 6 kilometers per second and increases through the lithosphere to reach speeds as high as a little over 8 kilometers per second. The S wave, on the other hand, travels considerably more slowly. This is why it's known as the secondary arrival, although it's also called the shear wave. Both of these waves show a dramatic and significant decrease at about 100 kilometers depth. And this has become known as the low velocity zone. We'll come back to the low velocity zone in a moment, but I'd like you to note that the asthenospheric mantle, which is very important, is about 200 kilometers thick and stretches from the low velocity zone to the uppermost boundary of what's called the mantle transition zone. The mantle transition zone will be the topic of our next video. So seismic wave speeds have been interpreted as evidence that there is plastic-like flow of the asthenosphere, and that this occasionally actually comes to align the axes of olivine crystals in mantle peridotite. So we have seen images like this one at the top right in our mineralogy textbooks, where we have the A, B, and C crystallographic axes. All of the items in red there are related to our optical content. And this picture from Lev in, I think, 2010, this picture from Lev shows that actually seismic waves, much like optical phenomena in calcite that we've already talked about, you can see that seismic waves travel faster in one direction through olivine than they do in the other direction. So if you take a look at this drawing of the olivine, and you notice that we have the Miller index 100, and here we have the 010 Miller index as being our slow wave direction. You might think about how this lower drawing corresponds with the upper drawing. And hopefully you will have noticed that the 100 direction, the fast direction, corresponds with waves traveling along the A-axis. This has been used in, this has been a phenomenon used to interpret wave speeds in a variety of studies. And I'm showing you one from Miyazaki et al., 2013 in Nature, where they were investigating how the alignment of olivine seems to change its orientation. So we might be having all of our olivine aligned with the fast direction coming out at us, or the olivine may be perpendicular to that. So this is a little bit like pickup sticks or colored pencils if you drop them on the floor. If you roll your hands over those colored pencils, they will eventually align perpendicular to the direction that your hands are moving. Whereas another way to do this would be to sort of cone the pencils in the direction that you're going. So there's a lot of complexity to the way that the olivines can be aligned in the mantle, but we know that without this plastic movement of the mantle, much like silly putty can be deformed, without this movement, we would expect the olivines to be randomly oriented and not to show a difference in wave speed. Getting back to the low velocity zone here, we're going to zoom in now so that we can see this better. And we see here in this diagram, again from the same textbook, we see that we have our crust being part of the lithosphere. And now we can clearly see that on average, the lithosphere is indicated to be about 100 kilometers thick. And our P-wave velocities reach their maximum speed in the lithosphere in the mantle portion of the lithosphere. So the thing to remember is that the lithosphere includes the crust and the uppermost part of the mantle. Then we have our low velocity zone stretching from about 100 kilometers depth to about 220 kilometers depth. Later on, we'll talk about the asthenosphere and these jumps in seismic wave speed, P wave speed in the mantle transition zone. But here, notice that I've indicated that the low velocity zone can be explained if about 1 to as much as 5% of its volume is molten magma. So 1 to 5% of the volume may be molten magma, but as we'll talk about later in chapter 11 of your winter textbook, we also need to think about when this molten material, how it's distributed, and what, why might we never have more than about 5% molten magma in one area. Okay, so hopefully you've already anticipated me and thought to yourself, oh, now I understand why this low velocity zone cannot be totally molten. If the low velocity zone were totally molten, then we would not have any S waves traveling through it at all. But we do in fact have S waves traveling through it. So that leads us to start thinking about the mantle behaving as if we have grains of olivine and pyroxene, and perhaps, depending on depth, garnet or spinel. And to think about there being a three-dimensional mush, really a three-dimensional, you could almost think of it as being like sand, a three-dimensional framework of crystals. But these crystals contain a little bit of space along their edges, and especially where these crystals meet at sort of a triple junction. And Hunter in 1987 was the first to start talking about how the nature of the melt on these crystals depends on the shape. If it is a really high viscosity melt, it also depends on the energy of the crystal surface. We would tend to, in the laboratory, find out that that melt would show a very a very high elevation or a very tall droplet. And what Hunter did was he defined what's called the dihedral angle, where he would look at the angle between the surface of the crystal and the side of that droplet. And that dihedral angle is being shown here in panel A, as well as being talked about in panels B and C. So when our dihedral angle is very high, we have a droplet that wants to stick together. It wants to pull together compared to the surface energy of the crystal. And so the melt will tend to accumulate in the corners or as droplets along the edges. However, if we have a droplet that is maybe less viscous, depending on its composition, it might form a flatter droplet, more like a droplet of water rather than a droplet of cold honey. The lower panel would be like cold honey. If we then have a flatter droplet profile, these droplets can become interconnected along the edges of these grains. And we would form an interconnected network of melt, which would then flow almost the same way water moves through the porous spaces of sand at the beach, and then be able to migrate toward the surface. Now, this image that I'm showing you is from the work of Marianne Holness. She's done just tremendous work thinking about in cumulate mafic rocks, kind of like our still water complex. She's done a lot of work thinking about how the last bits of melt accumulate and crystallize there. And that's because we can get larger amounts of those mafic cumulates from the crust, but we expect that the processes will be similar even in the mantle, although the pressure and temperature conditions would be very different. Well, if you want to think about the pressure and temperature conditions of the mantle, then we need to start using either computer models or other kinds of evidence. And so a group at the University of Maryland, including Zhu, has taken three-dimensional images of rocks, kind of like a really sophisticated X-ray of these rocks. And here they've just taken anything that was crystalline material and sort of been able to remove that. And what they're showing us is if you have only about 2% of melt in your three-dimensional package of mantle, that's going to look a little bit like where we see these red intersections at the edge of the box, but within our mantle chunk, it would look like these gray interconnected networks. If we increase the amount of melt volume to 5%, it will look more like the image at the upper right. 10%, we're looking at the image at the lower left, and then finally 20%. Now, once you have an interconnected melt network, we expect that that melt will start migrating up and out of the mantle. First of all, it's under tremendous pressure. Second of all, it's very hot, and it should be more buoyant than the slowly deforming mantle around it. And so the image on the right by other workers in this same group shows that beneath a mid-ocean ridge, we expect these anastomosing or fingering networks of melt to come to join, to carry the melt out of the mantle, and then that melt can get focused at the bottom of the oceanic lithosphere, for example, and then get focused at the mid-ocean ridge where this arrow number 3 is. So we're anticipating some of the later topics in the course right now, but certainly the seismic evidence, as well as the fact that we do not have continuous eruptions normally. Normally, we see short bursts of volcanic activity, and so that suggests that some process is controlling how much melt can separate and ascend at one time. So usually in this low velocity zone, we expect the situation to be like the upper leftmost image where we have 2% melt. So putting this all together, we're thinking about the low velocity zone, how it probably has 1 to 2% melt. At greater amounts of melt than 1 to 2%, we expect that that melt would become interconnected and able to aggregate in a network, perhaps even in a channelized flow. This has been fossilized mantle channels have been described by Peter Kellerman and co-workers in Oman, and we'll be talking about that later on. But here we have a cartoon from Tyrone, who did some computer modeling of this and published it in 2018. We also have both laboratory experiments as well as computer experiments taking a look at how does this process initiate, and then how quickly can it start to accumulate very quickly. So Erickson here was looking at 2 different phases, one that can move more rapidly than the other. And we see in the center here, we start to accumulate displacement. There is not any movement in the surrounding granular material, but then we get these anastomosing or dendritic networks forming. Eventually we get compaction as the interior part flows more quickly, and we can have a situation where we're getting a lot of movement of material, and we think in the mantle this would be moving both laterally as well as upward. So think of this as being sort of a top-down view. So if I'm going to summarize the low velocity zone, I just want to remind you of these points. Lithospheric plates are rigid, they are a mechanical layer, and they are moving on top of the asthenosphere. The asthenosphere is marked by having a low velocity zone at its top, as well as a zone where we see more continuously increasing wave velocity, suggesting increasing density. Both S waves and P waves do travel through the low velocity zone, so we know that it must be largely solid. The upper mantle is mostly solid, and we can explain the reduced velocity by having only 1% of the material be molten in the low velocity zone. We think that 1 to 5% ambient melt can account for the reduced velocities, but we think that usually we're down at the lower end of this range, because as we get more melt forming, that creates a situation where that melt can then begin to accumulate and move upward, and then the surrounding mantle that's left behind, the restite, can compact as that melt moves out. We can see that olivine and peridotites become aligned due to this plastic mantle flow. That is, as the lithospheric plate is dragged over the top of the upper asthenosphere, we can also have areas of that upper asthenosphere that show that the olivine have become aligned, perhaps a little bit like crayons getting aligned as our hands would shear over them. And then we're starting to see in computer modeling here done in 2018 of a granular two-phase. So the granular part is like our peridotite. The second phase could be more like our magmatic liquid. And that once you get some accumulation and movement of that liquid, it can continue accumulating the pockets of magma very, very quickly, and then we get compaction elsewhere. And this reminds me a lot of what happens when you put too much fluid on a shave ice. A little bit of fluid, that shave ice can hold together, keep its shape, even though the color shows us that there has been a fluid that percolated between the ice crystals. And then as we get a whole lot of fluid, that fluid pools in the bottom of the shave ice where all the yumminess is, and then we can get compaction and collapse of the granular material. Now, the only difference is with the shave ice, we would, instead of the fluid accumulating at the bottom, of course, the mantle is under such pressure that the magma is being squeezed out. So hopefully you understand a little bit more about the low velocity zone. It's an enormously important part of the Earth.